Okay. Hello everybody. Welcome to our summer lecture 2022 for the Kentucky Area Astronomical Society. My name is Dirk Gruppe. I am the vice president of the organization right now, and I'm if you're wondering where I am, I'm the chair of the Department of Physics, Geology, and Engineering Technology at NKU. And this is a good continuation of our summer lectures that Kyle Cook, who is a grad student at the University of Louisville, was offering during our meeting back in March or April. It was April, right? And so we started in 2020 with the first lecture, and then there were a couple of more on photometry, on galaxies. I did AGN. And so I'm very grateful that Kyle was offering to do a lecture over the summer, 4 lectures here on ultraviolet astronomy. And with this, I give it over to Kyle, and it's all yours, Kyle.
All right. Thank you, Dirk, for the introduction, and thanks to everybody who can be here. As you said, I'm a graduate student at University of Louisville, working with Bene Valverde. My research, which I won't talk about today, brings me into ultraviolet astronomy a lot. And I thought, for a number of reasons I'll touch on today, that UV astronomy may be a very timely topic to kind of discuss. So I wanted to kind of get into that a little bit today. As he said, it'll be 4 lectures, Tuesdays, at the same time for the next 4 weeks. And today is really just kind of a like getting our feet in and getting our feet in, getting them wet a little bit with just kind of the background and the history of UV astronomy. Um, Kind of disclaimer here, one thing that people may notice I seem to dance around a lot today is the actual science that we do with UV, because that's what I want to focus on next week. So this week is really just kind of the history, and I'll get close to some science and then I'll just jump right off of it. I'm not scared of it. I'm just trying to compartmentalize the lectures a little bit. So if you're looking for what we can do with UV astronomy, that is coming next week. Um, why is my screen not changing though? I guess I, there we go. So yeah, this is just kind of, my plan and the schedule for the next few weeks, where today we focus on the history and the motivation for why I'm even bothering you with UV astronomy. Second week, we kind of dive into the science a bit more. Week three, we talk about the instrumentation and kind of both what's existed and what is coming, with all building up to week four, kind of bringing it all home all together on why we're talking about this and where we're going and what the exciting things to happen with UV astronomy will be. All right. So then really kind of jumping in today is just my motivation, my wonderful blank slide, because I'm going to actually start with the lowest form of evidence, a nice little anecdote here. So I have had an interesting experience through academia that has not been a straight line path of high school, university, or high school, undergrad, and graduate. So I had quite a bit of time between my undergraduate and graduate careers. And I remember being in an intro kind of beginning level astronomy class and having to put together some sort of a talk. And I found myself looking for all sky images in every major, electromagnetic spectrum band. So radio, ultraviolet, infrared. And this was a very easy task. Even back then, I graduated undergraduate in 2010, so 15 years ago. Please don't tell anyone. Um, so even then, it was a pretty easy task. But when I hit ultraviolet, I could find basically nothing that resembled an all sky image. And the amount of searching I didn't really improve the results that I got. Um, so that stuck with me right away as a what's going on with the ultraviolet? Like I could barely have told you anything about galaxies at that point, but all of a sudden I automatically realized that something was different about ultraviolet and of what we had and what we did not have. So then now here we are 15 years later, and we would expect that the story may be quite a bit different than it used to be. And it wasn't, but maybe a few months ago, I happened to be looking at a textbook and found this fantastic image, which the caption says is the galaxy in all frequency bands. And off to the right, I just have the bands written out because it's kind of hard to see on this image, I think. And basically, what we have is we have three radio bands, two infrared bands, optical X-ray, gamma ray. And there is not even a casual mention about the missing ultraviolet. This text was published in 2022, so recently. And even better, if you notice, the image credit is NASA Goddard. So there's kind of this just missing ultraviolet that we're not even discussing. I will be the first person to say that an ultraviolet image looking through the dust lanes of the Milky Way galaxy is not going to be the world's most exciting image. If you are not sure why, don't worry, we will get there more next week. But um, it's just missing. And I think the fact that why would this image not be interesting or why would this image look differently than these is an interesting story to tell anyways, but we don't even have that conversation. So when I think of why should we talk about ultraviolet, it's things like this. It's just kind of what I like to think in my mind as just like the missing ultraviolet problem. Um, there are reasons. It is not a hateful, neglectful thing about ultraviolet, and as we'll see, a lot of ultraviolet astronomy has been done. But certain things like a good all-sky image are very, very hard to come by, whereas we have it in almost every other band. Um, so that's kind of my personal. The other reason for why we should be talking about this now is the story I just presented will be changing, and it should be changing soon. There are, I'm going to say, at least two very dedicated UV missions on the horizon. The first one is UVEX, which is a NASA Mid-X Explorer. It's the Ultraviolet Explorer. It is supposed to launch in 2030, and it will be observing in the ultraviolet, both photometry, spectroscopy, and we will get a lot of new information there. And as we move into the 2040s, that's where Habitable Worlds Observatory is proposed. And that is where things can start looking very, very different, where we have a lot of new UV information. Um, it is worth, I think, taking a short pause here to just say we all know that there is a lot of discussion going on about science funding, research and development funding. So when we see dates like this, how accurate are these dates? And I think the optimistic version of my answer would be is they are as reliable as they ever are. Um, Dates of missions shift, dates of missions change. Um, Hubble Space Telescope sat in storage for almost 4 years after its launch date because of the Challenger explosion. So it spent 4 years in storage that it was supposed to be up in the above the atmosphere observing. So these dates are always fluid, and as I know my advisor and others like to say, every mission has had its near-death experience. Um, these will, probably go through the same, and maybe we're seeing some of that, but I don't know. I don't know what the future holds, but I'm just the point I want to make is these things do happen, and it's not necessarily even unique right now, even if the situation is. All right. So stepping away from the UV directly and just kind of looking at the history of the electromagnetic spectrum and the discovery of it because I want us to put ourselves in a certain frame of mind, right? So there's of course the classic image of Isaac Newton with the dispersion of light through a prism, looking at the full rainbow being displayed and showing that all the colors that exist within white light. So you can find all these in the sunlight. So 1966, one of the fun things about looking for things historical is you start finding all kinds of fun things. So depending on where you look, 1666, 1667, I saw a 1672. So the exact date of this seems to float around a little bit, but 1666 seems to be the most common date I saw of Newton doing this experiment and actually showing that white light is a continuum. Then there's a bit of a break, right? So at this point, it's just light. Light is the rainbow, light is red through violet. 1800, here comes William Herschel, who did a clever little thing if you really squint at that image, and basically just put thermometers outside the red range and was able to show that the temperature increased in that range. So these became what he called his calorific rays, which eventually became what we call infrared today. Um, the natural conclusion there is, well, if we found something beyond the red, what happens if we look beyond the blue? So this is where Johann Wilhelm Ritter came in, and yeah, that's the best reliable picture I could get of him. So I don't know if we didn't like him. But he did that, and he looked at the blue, outside the blue, and of course, he found something interesting. And what he found, I will come back to because I'm going to continue through here. Radio, real quick, 1880s, late 1880s, Heinrich Hertz, big name that we know, obviously the classic image of the X-ray, and gamma rays, which we don't hear the discovery very much of, but all the way up into 1900, kind of fleshing out the rest of the more extreme ends of the ultraviolet spectrum. But back to ultraviolet, what was done is Ritter noticed that if you put, for instance, like a photographic plate or a photographic paper outside the blue end of the spectrum, that it exposed faster. In particular, it was silver chloride. And basically, what he saw is this, right? That you start with silver chloride and then it darkens and browns and even kind of decomposes as it's exposed to light. And he noticed this happening a lot faster beyond the blue, so into the ultraviolet, which he also gave, it spent some time being called chemical rays, probably because of the chemical reactions that you saw in the silver chloride. Um, Obviously, now we call it ultraviolet, but that was kind of our first ideas of where ultraviolet and that there was something else beyond the other end of the spectrum. It did not take astronomers long to realize that this was interesting, that there were astronomical possibilities for this wavelength of light. And there's a name that we've probably all heard as we've learned about atomic transitions, Lyman, Theodore Lyman in particular. And this is a large part of what he did is he looked and he kind of mapped out both the atomic hydrogen transitions and the molecular hydrogen transitions. Obviously, this was, lab experiments. This wasn't, using a space telescope or something of that nature. But he wanted to know as he kind of worked in the UV if he could actually manage to make a detection. So he did what astronomers did at the time. We tried to get over as much of the atmosphere as we could. So he climbed Mount Whitney in California and tried to take some observations. I noticed there's one thing I kind of said there that's not quite accurate, which is astronomers did at the time, because we really still do this today. If you were at the KAAS meeting. I think this year Tim Hamilton mentioned, his balloon experiments that he's done, putting things up to try and get above the atmosphere and make detections. At the time, the thing was to climb a mountain. So this is what Lyman did, and was still completely unable to detect ultraviolet signal from the sun, or the ultraviolet wavelengths from the sun. So kind of disappointing, because all of a sudden this has to be there. You know it's there, and it's completely and totally inaccessible to you. So this is, oh, I don't think that's the slide I meant to have there, but let's go for it. We'll come back to that thought. I'm sorry. Um, it is worth taking a quick moment just to define the UV. And this is probably the first place where I may run the risk of having some of the astronomers in the room look at me and be like, well, no, not actually. But taking the UV to be from the range 10 nanometers to 400 nanometers. And then that is kind of broken down into smaller subcategories in the same way that we break optical light down into red, green, blue. Um, or extreme ultraviolet, obviously butting right up against the X-ray there. You may notice that 91.2 seems like a very specific wavelength to make a cutoff. And again, we will talk about that later. The Lyman ultraviolet, going up to 115 nanometers, the far UV, the near UV, and then kind of UV ABC, which is what we tend to talk about here on Earth, because you can make a nice little cut somewhere in that area and say UVA and B mostly makes it through our atmosphere. So if you want to look at that, all right. But it's kind of in the C range is where we start getting it cut off and we don't have it coming through. The culprit, of course, you may already know, is O3, or ozone. So it's breaking that third oxygen off as those UV photons come in. They're able to strike the ozone, break one of the oxygens off, get absorbed, and then that new oxygen in the O2 can reform. And this is the whole idea of our ozone layer, which protects us from terrible things like ultraviolet radiation, which will do bad things to us. Um, I did want to take a quick moment to point out here, you may notice something interesting about the wavelength ranges here. You notice I have the near UV from 180 to 320 nanometers, and I have UVC from 100 to 280 nanometers. So there's a significant overlap between those two bands. There are kind of a couple reasons for this. One, this is how the reference I've put here, Linsky 2018, has chosen to break these bands down, and I am going with him because I believe that's reasonable. The other reason is it is easy to find astronomers that do UV that will tell you that anything longer than 200 nanometers is not UV. We can do that from the ground, mostly. This is where we start talking U-band observations as opposed to UV observations. So it may officially be UV, but you will also get some grumbling from UV astronomers if you call anything, longer wavelength than 200 nanometers UV. I say that because I'm in Habitable Worlds observatory groups, and I've literally watched it happen. So it's actually entertaining to watch it happen. Um, whoops, there we go. So this is where I thought my next slide was going to be. The atmospheric transmission. So um, Lyman, Theodore Lyman went up to Mount Whitney, took a look, couldn't detect anything. And as we said, it's because the ozone does absorb the UV. You have to get further. You have to get above the atmosphere, not just higher in it, not just above most of it. You really have to get above the atmosphere to make any detections of UV beyond the closest that U band that we talked about. And this is kind of where I'm saying it's got to be incredibly frustrating, right? You have all these ideas. You've done all this physics. You're Lyman. You've just, determined the Lyman bands and everything else. And you've gone through all of this and you can't even see from the stars what you want to see. And there's nothing you can do to fix that, right? You are early 1900s. You're not making a space-based observatory. It's not going to happen. So incredibly frustrating, I would imagine at least. Then came 1946, and a few really interesting things happened in 1946. Again, come with me to the time period. Let's kind of get in that frame of mind. We have, the world recovering from World War II. We've had the first kind of display of nuclear power. Um, Headlines from 1946. It was the first ever meeting of the United Nations that January. Um, Italy abolishes its monarchy. So before 1946, we were still talking, the Italian kingdom. Um, and something that doesn't seem like it belongs with having a kingdom is the first kind of electronic digital computer being turned on, ENIAC. So these are interesting things, but then you throw into the mix that Lyman Spitzer Jr. considers a space-based observatory. As a matter of fact, he put out the paper, Astronomical Advantages of an Extraterrestrial Observatory. This is literally Italy is getting rid of their king, and we are talking about a space-based observatory for the first time. This is History is full of these little moments that just don't seem like they belong in the same time period, but these are things that were happening at the same time. It is also worth mentioning one point of confusion here. This is Lyman Spitzer Jr. This is not Theodore Lyman. So it's just, the universe conspiring to be confusing that we have Lyman in both names, but they are wildly different people. So you may know we did not have a space-based observatory in 1946. Um, though I actually hope to show you and maybe surprise some of you that it may have been earlier than you expected, or that you think. So we put out a paper, we call for space-based observatories, and then we have the rise of space-based astronomy, kind of. Um, I think it is quite strong of me to say that UV was the thing that caused us to push for space-based observatories. But it was certainly a major factor and a strong motivator for it. Um, Spitzer's paper really specifically focused on the atmosphere itself and just getting above the atmosphere and the improved resolution and things of that nature, as opposed to specifically saying we need to do this so that we can observe the ultraviolet. However, Spitzer was quite interested in the ultraviolet. His research areas were things like the interstellar medium, things like hot stars, or just in general plasma physics, things that require the UV to study accurately. Um, I threw in a picture of Hubble here for one main reason. Well, two main reasons. One, it's a fantastic image. The other reason is just one thing I have heard recently is this idea that Hubble was our first space-based observatory. I heard that said, and I kind of started poking around a little bit, and I noticed if you, at least when I Googled it, the AI um, Google Assistant told me that yes, Hubble is the first space-based mission. Um, I'm going to tell you that's not true. And we'll see that more. But Hubble is an incredible instrument, but it was not the first space-based observatory. Um, the idea of a space-based observatory wasn't really widely accepted. It was, is the payoff worth it, right? So, okay, we can get UV, but we can get all the optical, we can get U-band, we can do all this stuff from the ground. Sure, the seeing would be better. Sure, our resolution would be better in space. But this is going to be a very expensive endeavor. Keep in mind, again, Lyman's or Spitzer's paper came out at the same time we're turning on our first digital computer. Spitzer is saying, hey, let's put an instrument in orbit that is capable of being communicated with from the ground, and we're literally just turning on our first modern computer. This is a big thing, and the development to get there is not a quick story. Um, so we didn't jump on space-based observatories right out of the gate. We did do UV mission or UV observations by rockets. Into the late 60s, early 70s, we started launching balloons, and we launched the AOA, or sorry, OAO, the Orbiting Astronomical Observatories. And these were kind of the originals. These were the first orbiting, put it up in orbit around the Earth and take observation instruments. Um, 2 out of 4 were successful. The first one launched, it was there. It lasted a short period of time, a very, very short period of time, I think on the order of days, and kind of went from UV all the way up to the higher wavelength. So our first thing we put up was to look at all the stuff we'd never been able to see before. Not shocking, I would do the same today. Um, the second one launched, but didn't make it up. Um, or sorry, I take that back. The second one I think was quite successful, and yeah, two was quite successful, and then the third one actually failed on launch. And then it was the fourth one that's actually numbered three, just because we continue to try and make things confusing. Um, which was called Copernicus, and it actually went up, it orbited, it was incredibly successful, taking observations, pointed observations. I think it got about 550 pointed UV observations. So this was a very, very, very successful mission. It did a very good job. And it paved the way for these three people to revolutionize space-based astronomy. So Lyman Spitzer, again, he made the initial proposal. He has been called in his day and currently still called the father of Hubble. He and John Bacall tirelessly hounded legislators to try and get funding. And Nancy Grace Roman, who was NASA's first chief of astronomy, um, got the name Mother of Hubble because she was every bit as involved as these two gentlemen. And it's strong to say that these are the three that made it happen, but these are the three very vocal, very public people that spent their time in front of congressmen making sure that we got it. To the point that there's a fun story about John Bacall when he saw that in the, I think, late 70s, that a space-based observatory was not part of the presidential budget request, and basically threw a fit until he got what he wanted. Um, so there's a lesson in here on talking to your legislatures to get science done. So this led us up to the age of Hubble. UV missions themselves. These are specifically non-solar UV missions, so things that we're not looking at the sun. You see Copernicus there, the OAO3. And then really the first big one after that is IUE, or the International Ultraviolet Explorer. I haven't watched the participants, but if Mike Carini happens to go on, he is literally the Kentucky expert on IUE. He worked on the mission. So this was really the first major space-based observatory for ultraviolet. Copernicus did a lot of work, but this was really the first UV ultraviolet or UV observatory, and it launched in '78 on a 3-year mission. Look at that date range. 81 would have been 3 years. This thing went almost 19 years. I think it was 18 years and 9 months, I believe. So it almost made it to its 19th anniversary since launch, and it was a wildly successful instrument. You see all these other things in here, and there's some interesting ones. Orpheus, I kind of like, and I want to point out a little bit on because Orpheus is, I think, a throwback to the idea of the sh space shuttles being used the way they were originally intended, which was really as a giant school bus. Orpheus was never meant to be put in orbit. It was meant to be carried up and down regularly in a space shuttle and just open up out of the cargo bay, be pointed around, observe some things, and come back down to Earth. It only flew twice. Um, Things like Challenger had a big role in changing the scope of the space shuttle program. But I want us to kind of look at two things on this table. I want us to look at the dates, and I want us to look at the wavelength range, the spectral range there. Um, and actually, I take it back. A third thing. There's almost in my mind a quick rule on when you look at a mission name, if it has S in it, it's probably spectrograph. So as you look through here, IUE had spectroscopic capability, IMAPS, the HST GSRH, the Goddard High Resolution Spectrograph. Um, Fuse is a spectrograph. STIS spectrograph. There's a lot of spectroscopic UV. There's not a lot of photometric UV happening. And if you look at the dates, you notice that they all kind of fall not super recently. In fact, in the last 25 years, we cut the list down to this, which is really just two HST, two Hubble instruments, and then Galaxy and Swift. Spear is actually a mission. I'll admit that before this, I had never heard of. It was a Korean mission, and I don't. It was up not even a year, and I don't know. I don't know the story if it failed or what, but I'm kind of curious, and that's something I'm going to have to go look at. I wish I had that information, but I literally discovered Spear last night. Um, the other thing you notice if you look at the red boxed range, there's not much variety within the wavelength range that we're looking at. If you look at earlier missions, you see things down to 7 nanometers. So looking at the extreme ultraviolet. Whereas everything recently, we've really just limited ourselves to the near UV and the far UV. And that's really as far as we've gone. Um, the image off to the side, just so you know, that is Copernicus. So that's our original kind of little UV detector there. So the question I put out then is, what changed? I make this point that in the last 25 years, the number of UV missions has significantly dropped, and the range that we're looking at is also significantly different. So what changed? And I put out four proposals on why this may be, some of it from my own ideas and some of it from discussions that I've had and heard. One is money. Two is technology. Three is the idea of a lack of interest in from the astronomical community in UV. And the last is really a question: were our UV missions a victim of their own success? So here's my short answers to these. Money, yeah, space-based missions are expensive. Um, Technological hurdles, UV detectors are notoriously low sensitivity. Our filters are notoriously low throughput. Um, I would like to be able to say and hope to convince you, I don't think lack of interest is one. The idea that just because the infrared, for example, has gotten a lot of attention over the last several years doesn't mean there's a lack of interest in UV. And this idea of it being a victim of its own success. The question kind of becomes, was UV science complete at the level that we could pursue? Did we have better technology that would make another multi-million dollar instrument reasonable at the time? So, stepping through these a little bit, money. Huh. This is obviously on everybody's mind right now who's paying attention to budgeting and everything. And the long story short is building missions are expensive, but so is running them. Because if we throw up a new NASA space-based mission every year, and say that that mission's going to run for 10 years, the amount of staffing and technological power and overhead to keep that mission running and operating continues to increase every single time we launch something. We're at an age that we're talking of discontinuing Hubble, which is terribly sad, but do we put up a better instrument that can do more? Or do we keep paying for this instrument that, has had a fantastic lifetime? I also threw this figure in from the American Academy of Advancement of Science, just kind of showing overall what's happening, which is that our discretionary spending as a country continues to go down. And by that I mean, that teal is your mandatory. This is your programs that you have, your Medicare, your things like that. We have to pay those things, right? These are funded things. But the money that we have left over, we can put where we want. That's our discretionary spending. And our non-defense discretional spending and the defense are decreasing over time, which means every year we look at a budget and we have to decide where the remaining money is going to go. Is it going to go to NASA, NSF? Is it going to go to these different places? But we have a smaller pool of money to start with. So I am not going into the politics of any of this. I just want to say this is not a political statement. This is a fact of our discretionary spending is decreasing. So if we want to know why our budgets keep going down, it's because the money we have to allocate to everything outside these mandatory programs is going down. Um, Looking at the technology, like I said, the filters are an issue. This is just a quick look at filters. So if you look, these are the Swift filters, and looking at the top image in particular, if you look over, these are the UV filters. There's actually only three filters here, even though you see six lines. Just so you know, one of the line is for the filter only, and the other line is filter plus detector and all the actual what you get at the end. So you can see these are peaking around a zero point 0.4 or 40% transmission, whereas our U band is peaking at zero point 0.8. So there is a cut of half in basically the throughput of our filters when we go to the UV, which means we're getting these UV photons, a lot of times a relatively low flux, and then we're throwing away over half of them on our filter. They're just hitting the filter and never even making it through. So this limits what we're able to do. This limits, for instance, our magnitude depth. The bottom image is literally the same thing, except it doesn't have the UV filters. But again, you just kind of see that things are peaking around the zero point 0.8. I have some questions about how accurate that is. I bet that doesn't include, yeah, sorry, that's the filter only. You can see for the B band here what happens when you include the detector, that it goes down dramatically. So technology issues have been a concern. A lot of great work has been done on fixing these issues, and we'll talk about those week 3. And are we a victim of our own success? So Galax was incredibly successful. Its mission continued to be extended on and on and on. It was incredibly good at what it did, and it gave us the closest thing to a UV all sky we have. UVEX, as with all missions, was not without its issues. Its resolution was really kind of not great, for instance, but it ultimately shut down due to we had to make a decision on what missions were going to be kept and what missions were going to go. And Galax didn't rank as high as it needed to stay on. It is worth saying that yes, some of the instruments had begun to fail and things like that. This also absolutely played into a role of its um, where it ranked. But there's definitely an idea that I have heard floated a lot by people that after Galax, we didn't need a new UV information, a new UV instrument. We really had what we needed from UVEX, or from, sorry, from Galax. And it took, now we're at the point that we have technology, and we probably got a little lazy about UV missions, and we probably should have done something, much quicker than we did. But we're definitely at the point that we can do something much better, and we can greatly improve on the work that Galax did. So now is certainly the time to start talking about it again. And is there interest? I mean, my short answer is yes. There is interest from people. If you study, here's an example, stars, galaxies, AGN, supernova, ISM, exoplanets, or comets, there is room for ultraviolet in your astronomy. And that is just a quick list. These are all examples of things, of people that are actually actively asking for UV now. So there is absolutely a need for it. And every 10 years, the decadal survey happens. And part of the decadal survey is to pass recommendations on what is the path forward for astronomy. And the decadal survey in 2020 put forward a recommendation for a NASA flagship mission that includes UV. As a matter of fact, it's to be UV to infrared, so a very wide range in wavelengths. And that's where habitable worlds comes from. So kind of the bottom line is we're constantly faced with the choice on doing science, and we want to do everything, right? If we could do everything, that would be great. We'd bankrupt every nation on Earth, and we'd do all of our science. But how do we maximize the science we can do with the limited resources, including money that we have, and kind of not true, but with existing technology? As I say here, NASA flagships in particular are about developing the new technology, about doing something new and not just staying where we're comfortable. It's about pushing those boundaries. And again, HWO is a NASA flagship. So it's not always new technology, but depending on your budget, it may very well be a new technology issue. So quick, quick run through kind of history of UV and why I think we should care about it. So just the quick thoughts on day one. UV astronomy continues to be important. It has been important in the past. It continues to be important. I think one of the big takeaways, if we think back to the efforts to get Hubble, science and progress requires us to really have an active role in the funding and decision making. If we just sit back and don't let our voices be heard from our elected officials, then they don't ever know that we want it in the first place. So, it's different when um, an organization like NASA is saying, "Yeah, give us money." Of course, that's their job. They need to pay their people. They need to do things. They don't want to fire people. They need to keep the lights on. They want the money. But when a constituent comes up and says, "Hey, I do science in your district, in your state, and this is really important, and this is why," then that starts making a difference to people. So if we kind of think back to the quick notes I made on is there an interest, is technology an issue, those are going to kind of be the next 2 weeks. So, week two is the science case. That's me trying to convince you that there is a need and there is an interest in astronomy for ultraviolet. And then week three is kind of some of the instrumentation and the advances that we're making that will make that science possible. Um, I will say week three, I will probably not be like pulling up like schematics and circuit diagrams and things like that. That's not the level of instrumentation I'm trying to go. So if that sounds scary or you don't want to do that, don't worry, I don't plan on doing that. And then week four is just kind of looking towards the future. And hopefully by the end of this, I've made a pretty convincing case to everybody that UV is important and we need to continue and get you excited for what is coming. And surprisingly, that took longer than I thought I was going to. So I am happy for questions or whatever anybody has.
Awesome. Thank you so much, Kyle. That was excellent.
Thank you.
So, any questions for Kyle? I guess people could have interrupted you probably anyway.
Yes, they could have. I actually meant to lead with that. If you had something you thought you should like, this needs to be answered now. Like, we're not super formal.
So I have a question. What makes the UV filter so different to the optical filters? I mean, I work with Swift all the time, as you know, and I'm used to the UV filters, but I never really realized that the transmission of the UV filters is only half of the optical filters.
It is it's more your kind of your coatings and your materials because
Mhm.
ultimately what you want is something that allows the UV through but blocks the optical. So it's kind of just down to finding the right materials, the right coatings that do that job well. And I've kind of said that part of my job here is to get through and not say anything about Swift that makes Dirk cringe. So I called Mike Carini the IUU expert. I'm going to or IUE expert. I'm going to call you the Swift expert and continue. Um, but you for instance, you're very well aware of that incredible red leak
Yes, yes,
on
in
Swift.
W1, yeah.
Yeah, and
Hmm.
getting that
Or
sharp ed those
W2,
sharp
in
edges
W2, yeah.
over that narrow range in the Swift filters in particular, it's tough.
Hmm.
So it comes down to the materials and kind of the construction of the filters themselves.
Okay, thank you.
And I do plan on touching on that kind of a little bit more as we go and kind of some of the materials that are used and
Okay, any other comment? Okay, no, sorry.
Can you hear me?
Yes,
Yes.
yes, we can hear you.
Okay. I'm was curious. I've heard about U bands and filters, and there's just a bit of a disconnect for me from what seems like a typical U band to all of the different ultraviolet bands,
yeah.
wavelengths.
Yeah, so U-band is kind of that narrow range of the ultraviolet that we can do from the ground. So it's beyond the blue, and it kind of does, like I said, does what we can do from the ground. But it doesn't really push us to where we need space-based missions. So that's where you kind of have like that U-band, which a lot of ultraviolet astronomers will be like, no, that's optical. That's not actually UV. Um, Official definition, sure it is, but
Mhm.
I don't know. It's kind of a turn your nose up at it type thing. It's more when you go get above the atmosphere. That's where we have like our near UV or far UV filters or the Swift filters, and then even further into the extreme ultraviolet. So it's just it is UV. It's just a different wavelength range because if you think it's that 10 to 400 nanometers, it's a pretty big band. So you kind of break it up in the exact same way we do with optical light, where I'll have a red filter, a blue filter, a green filter. It's all optical, but they're just different wavelength ranges. Does that answer your question?
Yes, it does. Thank
Okay,
you.
thank you.
Yeah, and it's interesting, when you said that people are saying, when you are in a U filter, it's not a UV filter. Well, yeah, if you go in the sun and you get sunburned, that's ultraviolet, right?
Yeah, there
So,
was a document being passed around on the Habitable Worlds Observatory Slack channel where it was, these are the science cases and this is, the wavelength ranges in ultraviolet that people are asking for. And it was sent out with the note, shame on you that called 200 nanometers wavelength or ultraviolet. So, and then I watched the fallout from that and it was just entertaining. Um, Trevor, I see your question. Do I know of any current advancements presently for UV filters? And the short answer is yes. They have done a lot to increase. Some of it comes down to just the techniques they're using to deposit the different materials on detectors and to build the filters and things of that nature. And yes, I will talk about that a bit more in week 3. So I won't go too much into that, but yes, it is an active area.
Bene has a question. And Clayton. All right, now we get the questions in. Excellent.
On that. Are there other missions in other operated by other countries? So these were all the US
Yes.
missions.
Yes. So I debated a little bit on this one in particular. So one thing that didn't make it on that table just because from the time frame it was um, done. There is a mission called AstroSat
Mm-hmm.
from India, which
Mm-hmm.
has done incredible work and does great UV information. It has been incredibly successful, and they have proposed AstroSat 2 to continue on that success. Um, I spent some time trying to look for a status update on where AstroSat 2 is and what's going on with that. And I could find precious little information about that. I spent some time going through ADS trying to look for recent papers, and beyond the initial kind of proposal paper, there's not much out there for AstroSat 2. So I chose not to include AstroSat 2 as a future mission just because I'm very uncertain what the status of that is right now. But AstroSat does have, in particular, a lot of information and good catalogs that are public and available to people. So, um,
Clayton.
Hey, there's a wonderful talk, Kyle. I heard you mention a lot about the push for getting UV and HWO, and I was wondering what the kind of angle is for trying to convince HWO people to put the UV filters on this new observatory that's mainly used for finding exoplanets and habitable worlds themselves. I want to know what the angle for using UV in those kinds of observations would be.
um, first thing I kind of want to say to that is one, right now it's not much of a push. There is a lot of interest in having the UV on there. Um, as we get later into development and budget decisions start having to happen and inevitably things get cut, then this is probably where people start, advocating for their favorite science project and things like that. But right now, we're so early in the planning phase, absolutely throw UV, ultraviolet, infrared, the kitchen sink, and everything else on this thing and see if it flies. Um, but the kind of motivation for the UV is twofold. So HWO, Habitable Worlds Observatory, the name itself it is a reflection of what the mission is for, but it is also chosen to get interest from the people with the money. Habitable worlds are exciting. But an equal part of habitable worlds is the transformative astrophysics piece of finding new things that we don't even know to ask the questions yet. Um, Sticking with the the exoplanets, there is a lot of effort to make HWO capable of detecting biosignatures, which means looking at the atmospheres of these planets, and you have a lot of important lines and a lot of important markers in the UV. And that would be the, I guess, kind of short, direct answer to that question is because we want to look at the atmospheres of exoplanets.
Thank you.
And I see Cameron had a question in chat. Why do we classify UV light from 10 to 400 nanometers? Why are the cutoffs at 10 nanometers and 400 nanometers? What separates EM waves in that specific range from other EM waves? Well, one end of that is a little bit easier than the other. 400 because that's basically where our optical ends, right?
Mm-hmm.
Optical is easy. Do I see it or do I not? Right? Now, on the other hand, I'm just going to say if you take Cameron, if we take you, me, and Bene, I'm throwing you under the bus with me, and put the three of us in a line and ask us to, rate our eyes, we're going to get different answers. Okay. Um, so sometimes exactly where people, our vision and things are is different. Same with what we hear and things like that, the frequencies. But, 400 nanometers is just kind of where we say that's the end of the optical. That's where we can no longer see a blue-violet light. 10, I would have to look and see if there's a historical reason for that. I'm honestly not sure off the top of my head. Um, I don't know if it was motivated by maybe physical processes, like where we expect these things to be, these photons to be generated, that there's something fundamental different about the processes. I'm honestly not sure. It's a good question that I didn't think to look into. So
Yeah, and I would argue that's probably more kind of not really fixed dominate, because you can also look in soft X-rays and you would say 12 nanometers is still soft X-rays, right?
yeah,
Mm.
it's a lot of, if
It's
you go poking around on the internet very much and you look at, like, say, the wavelength range for this band, you will find variations in the difference in the
right.
you'll see some things shift around, So, 10 to 400, okay, you may find another source that says a little bit different, like Dirk says, a soft X-ray, might be 10 or 12 nanometers. So
Right. So yeah.
it's a little loose.
Yeah.
Any other questions?
Okay.
I
Well,
think
Kyle, thank you very much. Well, we recorded this lecture, so we will post this on our website. So if you have some stuff you want to look up again, and we will send an email around as well to remind everybody that this will be available on the website as well. Thank you so much, and we will see you then next week again, Tuesdays, 1300, 1 p.m. EDT. And thanks again for doing this. And thanks everybody
thank you.
for
And
being
yeah,
here
thank you all
today.
for being here.
Yep. All right. See you guys next time. See
Yes,
you,
Trevor.
Kyle.
Yes, Trevor. Same link next week, I believe.
Yes, same link.
Okay.
It's the same one for every week.
Yep. All right.
Okay.
Thanks.
Thank you. Bye,
Bye.
guys.